Alright, so yesterday we were working with exponential growth and decay, so today we're going to be doing more with that, but we're going to be learning about specific types of growth and decay. So for this one, we have a little formula right there, but you might notice that there's a whole lot of variables in there and we don't know anything about them. So let's first find out what each one of them means. So the big capital A is the total amount. Can't see it?
No, you can make it bigger.
Yeah.
Just make the view. Remember, you do have it in front of you also to look at. So see where he's at, and you can also look at your paper.
There
So do
we
you
go. Is that better?
Okay, one for today right now. How about you just move up to Josh's for the moment? Okay.
Alright. So this kind of exponential growth and decay, this is mostly dealing with money, or like if you would invest in a bank, you would put so much in. After so much amount of time, you get a certain amount back. So this capital A, that is the total balance after T years. So this one right there, after you put in so much money, after X time, that's the amount that you will have either in the bank still or that you would be getting out. P, that first one right there, that is the original amount that you put in there. So if you go to the bank and say you want to start a savings account with $200, that's what the P is, the amount that you put in at the start of it. Next one, we have R. We've been working with lots of R's, so that is just the interest rate that you would get assigned. All kinds of banks have different interest rates, so it all depends on where you go. N, we notice we have two N's. One is being divided by, or R is being divided by N, and then we have N to the N power. So N is the number of times that you compound interest in 1 year. There's lots of different examples. So, like, for example, you can be compounded annually. And what does annually mean? Every year, once per year, right? It could be compounded monthly, so that means every month you get some interest in your account. So, if we do it annually, what would N be? If it's compounded once every year? 1. So is the number of times that interest is compounded in 1 year. So if we're doing it annually, we're only doing it once per year, so that would be 1. If we did it monthly though, how many times would we be compounding it in the 1 year? If we did it monthly? 12. 12, yep. So if we did it monthly, the N would be 12. So that is just what N represents, the number of times that we compound our interest with our account. And then the last one, T, usually stands for time, and then in this one, T is just the number of years that the account is getting money. So we look right over there, we have an example of it. It says write a compound interest function, which is just that thing right there, to model $15,000 invested at a rate of 3% compounded quarterly. So, first things first, we need to identify 3 things. We need to identify our P, our interest rate, and then our N, the number of times it'll be compounded. So first things first, what is our P value that we're being asked to deal with? What is the original amount that we put in? 15,000, yep, so we have that right there. So we can just write P equals 15,000. Then we have our R, what's that? It's this 3%, right? And we rewrite that as a decimal, so 0.03. And then the last one, we have, it says it's compounded quarterly. So what does quarter mean? 4, so that means our N would be what? Here, 3 and 4, so who thinks 3? For compounding it quarterly, 4 times in the 1 year, N would be 4. Because there's 4 quarters in $1, right? So the quarter for a year, that means there's 4 quarters in 1 year. So then our n would be 4. So we have all those. Right here, they just rewrite the equation as A equals 15,000. That's where our P goes. 1 plus our interest rate goes up top. Our number of times it's compounded goes right below that. So we have 0.03 divided by 4. And right up here we have to the 4t power, because right there it's n to the nt. So we just substitute our 4 in right there, but we don't know what our t is yet, do we? So that's where the next part of our problem comes in. So it asks us to find the balance after 8 years, right? So if we have this all rewritten out, they just go step by step. So they rewrite this whole thing, 1 plus 0.03 divided by 4, they rewrite it as 1.0075. Just drop everything down, and now they substitute in 8 for t. Why would they do that? Isaac?
Because t is the number of years and they're asking for 8 years.
We're being asked to find the balance after 8 years, so we just plug in 8 for our t, and then we solve our equation. And they've already done all the math for us, so we just switch this to the 32nd power. So 15,000 times 1.0075 to the 32nd power comes out to be 19,051.67. Is that a good answer yet? Just this number?
No, nearly.
Yep, we need a label, because what are we dealing with?
Money.
Money. So, yep, right after there, they write the balance after 8 years is, excuse me, $19,000 or $19,051.67.
Okay, I'm gonna stop us right here. I need everybody to get out their calculator. Everybody get out their calculator. This is a good spot, because you notice that what they did is they did not do the power separate. They didn't show what 1.0075 to the 32nd power is, and then go back and multiply times 15,000. They did it all in one step. So let's see if we can do it in one step and get the same answer they did, so that we can do that in our homework. So I would like everybody to, I'll show you which point, where I'm at. I want you to put this into your calculator, this step right here, the 15,000 times 1.0075 raised to the 32nd power. Let's see how your calculator handles that. Does it get the same thing as the paper shows underneath it? They've already rounded it to the nearest cent, yes. So would yours round to that?
Yes.
Okay. So if it doesn't work, we have to talk to your calculator. In other words, we got to make sure that you're going to be able to do this. So you cannot be working without a calculator. Everyone better have one. And anybody who could not get that to happen needs to raise their hand. We need to be able to have the calculator cooperate with us. So everybody got it? Okay, so can we, once we've done all the other steps, we do not have to do just the power like we were doing before. We don't have to take the 1.0075 and raise it to the 32nd power and write that big number down, and then go back and multiply it times 15,000. We're going to do it all in one step like this, okay? Anybody have any questions about that? Okay.
Alrighty then. So, Lizzie wants to cooperate. So now we can just move on to some practice problems. So it tells us to write a compound interest function to model each situation, then find the balance after the given number of years. So for number 1, what are 3 things that we found upstairs or up top that we should find? So we have 3 numbers or 3 options. So 17,000, 3%, and then annually. So what would our P be?
17,000.
Yep, 17,000. What's our R?
0.03.
0.03. Then it says compounded annually, so that means 1 because it's compounded once a year, so n equals 1. So just with these three values, we can rewrite our exponential growth equation there. So we can just write, there we go. A equals 17,000. 1 plus our interest rate goes up top over our n. That's all to the 1 to the t power.
Okay, notice class, you will not replace A and you will not replace T when you're setting up the function to model the situation. A and T will remain in the function. They do not get replaced.
All right, so before we move on, just want to clean this up. So we can rewrite E equals 17,000. What will go in parentheses here?
1.03.
1.03. And then 1 times t is just
2t.
t, so we can just write t up there. There we go.
In your notes, this is a good place to put, this is the what? What were we finding? The model. This is our model function for this situation. Okay, so would you write that beside Mr.
Yep.
Model function? The A is going to be in it, the T is going to be in it. We're just going to replace P, N, and R and clean it up. And that becomes our model function. Then we use our function to do what they want us to do.
So I'll just rewrite our model that we wrote. So 17,000, 1.03 to the t. So we're asked to find the balance after the given number of years, and what is the number of years that they tell us to find? 6, so we have that one right there. So we just rewrite our equation here, 17,000, 1.03, and we raise it to the 6th power because that's the number of years that we're asked to find the balance after. Then after that, we just plug it all in our calculator in one step.
So everything you see up there right now is important for you to have in your notes. Don't decide that what you want is better, okay? All of these are important pieces to these problems.
All right, so did everyone get the same number I did? 20,298.89?
Yes.
Okay, are we done yet?
No.
Nope, we still got one more thing. What are we dealing with? Money, so we gotta label it, right? So we have $20,000, $28,298.89.
Does our answer seem reasonable? Okay, why? You gotta round it, okay. What else? What's another reason that it seems reasonable?
It's an exponential growth function and it's larger than what we started with.
There you go. It's larger than what we started with. We were earning interest, so we better end up with a number larger than what?
17,000.
17,000, and we did. But yet, so it our answer seems reasonable, doesn't it? We always want to ask ourselves that question also.
All right, you guys try number 2 by yourselves.
Remember, getting it set up, don't worry about A or T. They stay A or T. We only care about P and R and N to start with. That's not, you shouldn't circle it yet, it's not cleaned up yet.
Okay.
Double check your model, make sure your model is correct.
Isaac?
I got 1.0075.
Does everything else match? Do you have the same R value and the same N value?
Yes.
Okay. And so here's the deal.
Oh, wait, no, that's what.
Does a division come before addition? So sometimes we have to do the,
Anderson?
I'm just curious, why can't we put in each way for T? The 8 was 32,000, parentheses 1 plus 2, or that one, why can't we put 8 in
The reason is, let's go back up. It's because we're asked to write the compound interest function model. So that's why we don't put the T in right away, because this is just the model that will let us put in any amount for T and then be able to get the.
so in our model are the things that cannot change. So we're not gonna change how much they start with. We're not gonna change how often it's compounded, and we're not gonna change the interest rate. So in our model, all of those things that are non-changeable are in there. But you can change how many years you invested for, can't you? Yeah, so the T is why we need the T in the model, and then we replace the T once we're supposed to find it for a certain number of years.
Write it down.
Isn't 1 plus 0.0005, isn't
This is the model.
isn't that 1? Unless I'm wrong.
Yeah, let's put it down. Yep. Okay, does everyone have the same model that I do? This is the model for our function, right? So in your homework, if they ask you to write the model for a compounded interest function, you should have this part in there too, right? So once we have that, we have to find what the balance would be after a certain amount of time, and what is that one? 8 years, so we just rewrite it. Just rewrite it up here for ease sake. Or to the T. Then we just plug everything back in with 8 this time.
Yeah, extra 0 here.
I do, don't I?
Okay, we got lots of people who are not gonna get the point of the model function on a quiz. So the model function is circled in the bottom left. That is, we do not put 8 in for t while we're finding the model function. So you need to have an a and a t in your model function. Then you're going to use your model to help you find what they're asking you to find. So there's people in here who are going to lose a point on an assessment for not having the correct model function. And tomorrow when you're correcting, it's going to be confusing to you.
So, did everyone get the same number I did? 26,979.99. Don't hear anything saying otherwise, so am I done here?
No.
Nope, still got that last step, and that is to
Add a dollar sign.
dollars, because we're dealing with money, right? Wish I had this much money. Alright, so we can put A equals. So those are the two parts that we should have for an answer, because we have to have the model for our function. That's what the bottom left one is. And we have to have the amount that will be at the end of our balance after whatever time they give us. Okay? Does anyone have any questions? Before we go to the back page. There it is. Next. There we go. Okay, so on the front page, we were dealing with exponential growth, and now we'll be doing a special function that deals with exponential decay. And this is involving the half-life of substances. It usually involves elements. So have you guys ever heard of a half-life, like in one of your science classes? No? Some of you have?
Biology, they actually did talk
Mhm.
about
Yeah.
half-life
Oh,
and that stuff.
well, wonderful. So here we have just the general function for a half-life scenario. So you have 3 variables this time. So just like our other one, A is the final amount that we would have after so much time. P is the original amount we're given, so just if you have a pound of something, that would be your starting amount. And T, this is sort of the confusing part. Usually T just stands for the amount of time that you're given. For half-life, T is the number of half-lives in a given period of time. So, for example, if something has a half-life of, I'm just gonna say random number here, 1 minute, over the span of 5 minutes, how many half-lives would be in there? Something has a half-life of 1 minute. In the span of 5 minutes, how many half-lives would happen?
5.
5, right? Because if there's 1 minute, that's 1 half-life, 2 minutes, there's another one, 3, there's 1 more, and it just keeps going, okay? So, here we have a little example. It says Isthmus 212 has a half-life of approximately 60 seconds. Hey, look, we got it right. Find the amount of Isthmus 212 left from a 25-gram sample after 300 seconds. So the first thing we do is we have to find T, and this is the number of half-lives that will be in the whole amount of time that they tell us. So the total amount of time that we have is 300 seconds. And then the approximate half-life is 60 seconds. So to find the number of half-lives that would be in that span, we just take 300 divided by 60. So what is 300 divided by 60? 5. So we get right there. So that means that there's how many half-lives of Isthmus 212 happening in 300 seconds? 5. So we got that. After we find our T, we substitute both of our P and T values. What's our P value for this problem? What's our original amount that we start with? Left from a something tangible.
It tells you how many grams.
Find the amount of Isthmus 212 left from a 25-gram sample. 25. So 25 grams would be our P value. So we have our P value, we have our T value. Why aren't we finding an R value like we did on the front side? Where would the R go in this equation there? Where the 0.5 is, right. So that's where the half comes in for half-life. So after 60 seconds for Isthmus 212s, whatever you start with, after 60 seconds, you're gonna have half of that. After another 60 seconds, you're gonna have half of that, what you just started with there. So we're always going down by 1/2. We're always having a constant ratio of 0.5. So that's where the half-life comes in. So there, we just substitute our P and T value. 25 is our P, 5 is the T that we found there. So just plug all that in your calculator. You guys don't have to because it's already on your notes.
Let's just see if it works in our calculator. Let's do
There you
that.
go.
That's 25 times 0.5 raised to the 5th power. Let's make sure you get the same thing your paper says. Make sure our calculators are cooperating again.
Yep.
This is your opportunity to make sure you have a cooperative calculator. Do you? Okay, let's start practicing then.
All right. So it says write an exponential decay function to model each situation. So we're going to have a model for part of our answer. And the second part, find the value after the given amount of time. So we're going to have 2 parts. First things first, we have to find what 2 variables? Our P value. Help if I had a pen. P. And then what's our other one?
T.
T. So what is our P value for this practice problem?
30.
30. So we have 30 grams, so our P is 30. Now T is the number of half-lives that are going to take place in the given amount of time. So The half-life is 8 days. And we're asked to find how many, or how much is left after 24 days. Brighton, how'd you get that?
24 over 8.
24 over 8. So over the course of the full 24 days, if its half-life is 8 days, 8 goes into 24 3 times, so that's where he got the 3 from. So, have those two values. What do we do next?
Okay, but wait a minute, we really are gonna use the T in the model, okay?
Okay.
So go ahead and set up your model next.
Okay.
So in our models always, here's how we know when we have a good model. In our model is things that will not change. We're starting with a 30-gram sample. It's got a half-life, that's where the 0.5 comes from. So our model is going to stay, that's our model. We're not going to replace T in our model, we're not going to replace A in our model. Okay, so circle that and put the word model behind it. It is your model. Then you're going to use your model with your T value you found to figure out the A, the amount left after those 3 half-lives. Okay, let's make sense of this. I have to do this, I'm sorry, Mr. Conlon. We start with 30 grams. 8 days goes by. How much is left of that? What do we have at this one? It's iodine? Iodine 131. How much iodine 131 is left after the first 8 days? The answer's not up there. You gotta think this. So they've got this iodine 131. We start with a 30-gram sample. 8 days goes by. That's its half-life. Half-life means what?
Half of it's gone.
Half of it's gone after that 8 days. It has decayed. So how much is left after that first 8 days? 15 grams, right? Okay, now another 8 days is going to go by. Now we're up to how many days, by the way? 16. So a second half-life has gone by. We have that 15 grams, and now it's gone through another half-life. So now how much is there left? 7.5 grams are left. But we've only gone 16 days. We got to go through another half-life of 8 days, right? So after another 8 days, another half-life, it was at 7.5. Now what should it be at? Half of 7.5, which is 3.75, right? Isn't that what we get? 3.75? Did we get a good answer? Yeah, make sense of what we're doing here. Okay, so it went through 3 half-lives. We just took a little shortcut using the model.
All right. So everyone got 3.75? Are we done yet? Nope, we gotta label it. What are we dealing with in here?
Grams.
Grams, so our answer would be 3.75 grams. All right, you guys do number 4 by yourselves.
Show your work getting your T value. Don't just write down something for T. Show how you got it. It's important. Remember, what does the model, what's the only variable that gets replaced in the model?
P.
P.
Okay, did everyone get the same model as I did? A equals 40 times 0.5 to the t.
Yes.
Because your starting value is 40 grams, just substitute that in for P. So your model always has A and T, right? So after that, to find the amount after 60 hours, now is when we plug in our T value. So times 0.5 to the fourth. And that equals what? 2.5. 2.5 what?
Grams.
2.5 grams. So, is everyone okay with exponential growth, dealing with interest or compounding interest? Is everyone good with half-lives, exponential decay, things like that? 0.5. Since we're dealing with half-lives, our rate is always going to be the root of 1/2. So, if no one has any questions,